I have one more example that I want to talk about, and this has to do with what are called catenary curves, which I've all my life called catenary curves. But these are curves that appear in nature all the time. And so here's two examples. So if you were to think about a spider web and think about what's the curve that's determined by the spider web here. Is it a parabola? What is it? And it's actually the same curve that's determined whenever you have any sort of hanging object that's between two poles. And actually it happens to be the same curve as the St. Louis Arch. Okay, so it's the same curve, just upside down. And so I want to figure out what exactly are these curves. They're called catenary curves or catenary curves. And it turns out that these can be studied using some physics principles. So I'm going to skip the physics derivation, but just give you the differential equation to solve. And it turns out that the differential equation to solve it involves the density of the rope. It involves the tension of the rope or the chain or the string or whatever it is. And so we'll need variables for both of these. So let's say that a rope has tension T. So it'll be a constant, and density rho, also a constant. And then let's let, just for convenience, let's let A be the tension over the density. Then the rope, it turns out, for some physics reasons, then the rope satisfies the following differential equation. So A times the second derivative of y with respect to x is equal to the square root of 1 plus dy dx squared. Okay, and here we're going to have y prime of 0 equals 0. Here y equals f of x is going to be the curve that's determined by the rope or the chain or the string or whatever. Okay, so we need to figure out how to solve this differential equation. And even though this looks like a second order differential equation, this is actually a first order differential equation that you can solve with substitution. The substitution we're going to make is that u is dy dx. And if u is dy dx, then du dx is the second derivative. And it turns out that that's going to imply that our differential equation is going to become a du dx is equal to the square root of 1 plus u squared. This is separable now. Remember, a is a constant. So we're going to end up with a times 1 over the square root of 1 plus x squared dx. And that's going to be equal to, what? I made some silly mistakes here. This should be a u. I wonder, I don't know what to do next. So this is a times 1 over square root of 1 plus u squared du. That'll be equal to dx. There we go. And now we'll integrate both sides. And we need to think about how do we integrate the left side. And you could do this a few ways, but this is basically just a trig substitution. You would let u be tangent theta. You could go through and you could solve it that way. This is going to be inverse hyperbolic sine. So this is one way to do it, of u, times, let me write that a little clearer, of u times a. And then on the right side, we're just going to have x plus c. And then we could divide both sides by a. So this implies that inverse hyperbolic sine of u is going to be x over a plus c. We can just absorb the a into the c at this point. Take hyperbolic sine of both sides. So u is sinh of x over a plus c. And u, remember, was dy dx. So what we have to do one more time is integrate both sides. So we get sinh of x over a plus c. And therefore y is equal to another 1 over a cosh of x over a plus c plus possibly another constant d. And so it turns out what's happening here is that these curves that we were looking at are not parabolas. It turns out that they're hyperbolic cosine curves. So this is the curve that you get whenever you have a hanging rope between two poles. So if you are driving down the highway and you see two utility poles and you see the wire kind of hanging down a little bit in between, that's a hyperbolic cosine curve, a catenary curve. Okay, so those are the curves that it turns out we get when you have this phenomenon.